So a very good afternoon to you all present here. And I could see our resource person, Professor Farnsworth here. So I request him to please start from where he left yesterday.
Yeah.
Dr. Farnsworth.
Yeah. So can you see everything properly?
Yeah.
Yeah, okay. Hello again, everybody, and thank you and welcome back to the second part of my talks. Today what I'm going to be doing is I'm going to be continuing on where I left off last time, and that is I want to be introducing Dinkin diagrams, and then I want to have a look at using Dinkin diagrams to find subalgebras in Lie algebras. So this should be the fun part of the talk. So last time it was mainly algebraical. This time things are going to be much more geometric and intuitive. Okay, so if you remember at the start of my last lecture, I told you that the ultimate goal was to find some nice tools for analyzing Lie algebras that continue to make sense and easier to use in particular for large algebras. But if you remember, in the last lecture, we didn't really achieve that goal. Right? The last lecture focused on constructing root diagrams in a really algebraic fashion. Right, so we still had to calculate all of the commutation relations. We constructed explicit representations. We searched for eigenvectors and eigenvalues, and then we plotted the eigenvalues. And so this procedure seems to be following or doing everything that we're trying to avoid. Right? It really doesn't seem like a procedure that's going to scale well to larger algebras. Secondly, at the end of last lecture, at the end product were root diagrams. And the dimension of a root diagram depends on the rank of the Lie algebra that you're considering. And so it doesn't seem like drawing root diagrams is going to be something that we can continue doing for higher and higher rank Lie algebras. And so it seems, at least naively, that we're heading down the wrong track. And it seems that this isn't going to be a fruitful direction. And so I want to fix up both of these problems in today's lecture. So in particular, rather than a geometric approach, I'm going to be taking a much more algebraic, rather than an algebraic approach, I'm going to be taking a much more geometric approach, which avoids a lot of the sort of calculations that we had to do last time. So that sort of circumvents the first objection. And secondly, I want to introduce Dinkin diagrams. And Dinkin diagrams are a way of encapsulating all the information in a root diagram in a two-dimensional picture. So all Dinkin diagrams can be expressed in 2 dimensions. And so regardless of the rank of the Lie algebra that you're considering. Right? So that's roughly speaking, what we're going to be covering for this lecture. So what I'm going to do is I'm going to begin very, very briefly with just a recap of what we did last time, just very, very shortly in 2 quick slides, and then I'm going to jump into the content. So just to remind you, last time we came up with a recipe for constructing root diagrams. And the recipe went a little bit like this. First of all, we started with some Lie algebra represented on some vector space. And what we wanted to do is we wanted to find a nice basis for the algebra and a nice basis for the vector space. And so for A, the algebra, we selected the Cartan Weil basis. And then for V, we constructed a basis as eigenvectors of the Cartan subalgebra of A. And so the basis for A was the Cartan Weil basis. The basis for V was a basis of eigenvectors of the Cartan subalgebra. And once we had these bases, we found a nice way of labeling the basis of V in terms of its eigenvalues. Right? So we grouped these eigenvalues together into weight vectors, and then we plotted the weight vectors in Rn, where n is the rank of the initial algebra. Okay, so this is the full prescription of what we did last time, right? And in particular, when we're looking at adjoint representations, we call the weight diagram a root diagram. Okay, so just a quick example that summarizes all this. So for SU2, we can write out the generators in the Cartan vial form. And then the adjoint representation is a representation of these generators themselves on themselves, right? So on these elements, which we can write out as 3 by 3 matrices in this case. And if we focus in on the Cartan subalgebra element, right, its eigenvalues are 1, 0, and -1, which go into our root plot here as our roots. Right? So that's a quick encapsulation and example of everything we did in the last lecture. All right, so now let's try to throw all of that algebraic work behind us to a certain extent, and let's have a new look at these root diagrams. So on the screen here, I have the SU3 root diagram. And this diagram, if you focus in on these 3 roots here, -1, 0, 0, 0, and 1, 0, these 3 elements look very similar to what you see in the SU2 root plot. And that's because this is an SU2 root plot. These roots correspond to basis elements which form an SU2 subalgebra of SU3. And that's very curious for 2 reasons. First, you can see directly, you can find subalgebras directly by looking at the diagram, right, itself. But secondly, if you remember in the last lecture, I told you that when we separate our basis, when we construct our Cartan vial basis, the basis separates into a Cartan subalgebra and then what we called ladder operators. And the function of the ladder operators was to map you through a representation, right? You can act on basis elements of the representation with the creation and annihilation operators and get new elements in the basis. So a curious question arises. You can ask, if this is an SU2 subalgebra, right, then how do the elements of this SU2 subalgebra act on these other roots, the other basis elements associated to these roots? Right? How do these guys here act underneath this SU2 subalgebra? And of course, we could go ahead and we could just calculate how they act. So for example, the basis element associated to this root here is E plus, E1 plus, and we can ask how it acts on, say, E3 plus, maps it to E2 plus. Right? But I promise you we're not going to do too much more in the way of algebra, so I'll just give you the answer. And the answer is the following. With respect to this SU2 subalgebra, these 3 elements here, these 2 roots transform as a doublet. They sit in a doublet representation underneath this SU2 subalgebra. And similarly, these pair of elements as well, they also sit in an SU2 in a doublet representation underneath this SU2 subalgebra. Now, at the root, since this is at the 0, 0 point, the origin, since this is a rank 2 algebra, there's also a degenerate root here, and the degenerate root sits in a singlet representation underneath this SU2 subalgebra. And it's quite curious, if you look, these elements that sit in a doublet, they sit directly above where you would put crosses, right, onto this SU2 weight diagram to indicate a doublet representation. And similarly, the singlet representation sits exactly where you would expect it to be. And so you can imagine if you had a light shining from up here down onto the plot, then the shadows cast by these points here would sit directly above where you'd want to place their weights on a weight diagram for a 2-dimensional representation of SU2. So you might ask, is there anything special about this SU2 representation? And the answer is no, of course. And in fact, if you connect any 3 roots that go through the origin in this fashion, they will also form an SU2 subalgebra. And you can then ask, how do the remaining roots transform with respect to this subalgebra? And the answer is, if you look, sort of tilt your head, you see that these two elements, they sit in a doublet representation underneath the action of this SU2 subalgebra. And similarly for these, and again, there's a singlet at the origin. So it turns out that this will generally be true, right? If you have a Lie algebra and you find a subalgebra, then all the remaining elements will sit in representations of that subalgebra. And you can see that that will be true, right? If it was the case that this subalgebra mapped elements from outside from up here into the subalgebra, then it wouldn't be a subalgebra, right? So the fact that this is a subalgebra means that these elements transform into one another, and so they have to sit as representations of this subalgebra here, right? And this will be generally true, not just for SU2 subalgebras. So this is quite a powerful fact, right? And so what we want to do is we want to see if we can use this observation to build new root plots, right? So in other words, let's try to build a new rank 2 root diagram by inserting roots. So here's the recipe. We're going to start off by writing down a rank 2 root diagram, and we're going to insert an SU2 subalgebra. Right? And now we want to insert roots into the diagram to find new root diagrams, and we have to insert them in such a way that they sit as representations of this original SU2 subalgebra. Okay, that's the rule. And we're going to try to classify all of the rank 2 Lie algebras in this fashion. So for SU3, right, we were looking at doublet representations underneath this SU2 subalgebra. So the most obvious thing to look for now is singlet representations. So let's do that. So we start with an SU2 a rank 2 root diagram, and we begin with an SU2 subalgebra to start with. So these three elements labeled -1, 0, 0, 0, and 1, 0, they form an SU2 subalgebra. And now we can insert some roots that sit in singlet representations. Right? They sit above this 0 here. And I told you that any two elements that meet through the origin have to form an SU2 subalgebra. And so we also need to include a 0 here as part of this SU2 subalgebra. Okay, so if you look, you'll see that this forms an SU2 subalgebra under which these guys act as singlets, and these guys form an SU2 subalgebra under which these guys act as singlets. And so what we have is two SU2 subalgebras that don't talk to one another. And in fact, this is a consistent root diagram. And it corresponds to the semi-simple Lie algebra SU2 plus SU2. And you can have a look at the counting. There are 1, 2, 3, 4, 5, 6 basis elements, as you'd expect. This is 3 basis elements in here and 3 basis elements in here. Okay. So this is a consistent root diagram. Let's see if we can go further. So we've looked at singlet representations and doublet representations. Let's look at triplet representations. So once again, let's start by drawing up a diagram and including to start with this SU2 subalgebra. Right? And then let's try to insert roots in a triplet representation. And of course, once you add a root, you have to add units negative as well. And so what you can see is these elements here, these 3 elements form a triplet underneath this SU2 subalgebra. And if you tilt your head, these elements here form a triplet underneath this SU2 subalgebra, and so do these guys. Right? So you might ask me, well, look, I've put labels of where these roots are. Why should this be 1, 1? Why can't I put that up at 1, 17 or something? And the same as here, this one at 0, 17. The answer is if you turn your head, right, any 3 elements that go through the origin have to form a subalgebra. The remaining elements have to sit in a viable representations underneath that subalgebra. So that constrains what values these roots can take. Okay. And so you can see that these two elements sit in an SU2 doublet underneath this subalgebra here. These elements act as singlets underneath this SU2 subalgebra. And in fact, this is a consistent root diagram. And it corresponds to a 10-dimensional, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a rank 2 10-dimensional simple Lie algebra. This is SO5. I should have written that. So, it's down the bottom. Okay, so this is very nice. Let's see if we can go any further. So we've looked at singlet, doublet, and triplet representations. Let's have a look at 4-dimensional representations. So we start again, we draw up our 2-dimensional root diagram, and we start off by writing down an SU2 subalgebra. And then we ask, can we find representations that sit as 4-dimensional representations underneath this SU2 subalgebra? Okay, so we start by adding
Excuse me, you are not audible.
Hello, Dr. Farnsworth. Hello. Hello. Let me do something. Let me remove him. He will again join, right? Or I'll send him a message. Actually, he was connecting from his mobile. So in some of the handsets, if the phone call comes, your internet connection gets disconnected. I don't know. That may be an issue. Looks like some major issue. Dr. Farnsworth?
When did I drop out? How long have I been gone for?
Yeah, almost 5 minutes.
Almost 5 minutes. I apologize. So now I'm on the proper internet connection, so I should have no more problems from now. Could you tell me? Could you tell me what the last slide was, or where I left off?
Sorry, slide number. I didn't check. Any of the students who have noticed the slide number?
Or could you?
You were showing the four-dimensional representation.
Yeah, but slide number we do not remember actually. Just you just show the pages. We will say very well.
Okay. Have you seen this yet?
Please start the presentation.
Oh, sorry. My apologies. My apologies, everyone. I didn't plan on this. Have you seen this yet? Can you hear me?
It is here, yeah. Yes, yes. You are discussing this part, yeah.
So have you?
Yeah.
So which one of these have you seen? Have you seen this?
Go back.
Yes, we have seen this.
And have you seen this one?
Yes, also this one.
Can you tell me when to stop?
Yeah, up to this.
Yeah.
So have you seen this?
No.
You are discussing this one.
Oh, okay. My apologies. So my apologies, everyone. I didn't plan on this. I'm at a hotel and the internet just cut out. Okay. So I shouldn't have any more further problems. So what I was saying was, we want to be constructing root diagrams making use of this trick, and we've had a look at two-dimensional representations, singlet representations, and triplet representations. So now we want to continue, and the obvious thing to do is to look for four-dimensional representations. So what we do is, again, we start with our root diagram, and we introduce our SU2 subalgebra, and we ask that the remaining roots sit in a four-dimensional representation. Now, once we've added in these roots, of course, we have to add in the negatives, and you can ask, is this a consistent root diagram? And the answer is no, right? If you consider this SU2 subalgebra through the origin here, what you'll find is that you have roots here, these three roots, that don't sit in a triplet representation. Right? They don't sit in a triplet representation because they're not symmetric about the origin. Right? If you imagine a light up here shining down, the shadows that would form from these three elements here would not sit where you'd put the crosses on this SU2 root diagram to indicate a triplet representation. And so what you can do is you can try adding in another root to form this into a four-dimensional representation underneath the SU2 subalgebra. Right? In fact, this makes up a consistent root diagram. Right? So you can go ahead and you can check for yourself. This is a consistent root diagram. And so this corresponds to a rank 2 14-dimensional Lie algebra, and this is the G2 root plot. Okay. And so you might wonder, can we just keep doing this? Right? Can we now look for a 5-dimensional representation? And the answer is no. This turns out to be the last consistent rank 2 root diagram that you can write down. If you tried to add a look for 5-dimensional representations, you would find that the geometric restrictions stop you from writing down a consistent root diagram where every root sits in a valid representation underneath any SU2 subalgebra. So this is quite nice. It turns out that for every Lie algebra has a unique root diagram, and so we can think of using the root diagrams to classify the Lie algebras. And we could go ahead for rank 3, and in 3 dimensions we could draw up the root diagrams. But unfortunately, for any higher than 3 dimensions, it starts getting quite difficult to draw these diagrams. And so you might wonder, this technique is of course very beautiful in the lower dimensions, but does it continue being useful in higher dimensions? And in order for this idea to be useful in higher dimensions, I need to introduce some further tricks. And the trick I want to introduce is the following. So if you look at this root diagram for SU2, you see that there are 12 non-zero roots. And this is a 2-dimensional plot. So it's obvious that these are not all going to be linearly independent. It turns out that for a rank n Lie algebra, its root plot will have n linearly independent roots, non-zero roots. Right? And so what we can do is first of all observe that for every root there's a corresponding negative root. Right? So really we only need to work with half the roots. Right? So what you can do is you can bisect the plot. Right? Draw a line down the middle of the plot and separate the roots into what I'll call positive and negative roots. Which ones you call positive and which ones you call negative, that's just convention. But so I've chosen to call these guys up here in the upper half plane, roughly, the positive roots. Now, once you have your positive roots, notice that they're also not linearly independent, right? And it turns out what you want to do is you want to find what are called the simple roots. Simple roots are positive roots which cannot be constructed as a linear combination of the other roots with positive coefficients. So for G2, it turns out it's these 2 roots here. So these 2 roots that I've indicated in red cannot be constructed from the other roots with positive coefficients. But once you have these 2 roots, right, you can use them to create the remaining roots by just taking linear combinations. So for example, if I take this root and add it to this root, I'll get this root here. If I add one of these roots to 2 times this root, I'll get this guy here. These 2 added together will give you this guy here, and so on. And in fact, it turns out that that every root diagram is completely characterized in terms of its simple roots. You can reconstruct the entire diagram from just the simple roots alone. And each diagram is characterized by the length of these roots, right, and the angle between them. Right? So what you'll see is in this G2 diagram, this root is longer than this root. Right? The length of this root vector is shorter than the length of this root vector. And the angle between them is 150 degrees. Right? And those 2 pieces of information characterize this root diagram. So let's have a look at another example. This is the SO5 root plot that we saw earlier. And again, this has 2 simple roots. Right? So what we do
Professor?
is, yes?
Is there any way that I can predict the number of the simple roots? I mean, is it this number of the Cartan subalgebra dimension that here is 2 simple roots because I have 2 Cartan subalgebra dimension? I mean,
That's exactly correct. So the number of simple roots will correspond to the rank of the Lie algebra. That's exactly correct.
Okay.
So this is SO5 is again a rank 2 Lie algebra, and there'll be 2 simple roots. And so what we can do is we bisect the plot by drawing a line through it. And it turns out that these two are you can go through and work this out for yourself, and please do. Please go through and have a look at these and convince yourself that these are the 2 guys that can't be constructed from linear combinations of the other elements with positive coefficients. Right? But what I can do is, if I take this guy and I add them together, I get this guy. This one plus 2 times this one will give me this one. And so we can reconstruct all of the roots from these simple roots. Right? And if you have a look, these are the same. This root here is longer than this root. Like the length here is longer than the length here. And the angle is 135 degrees. Right? So there's 45 degrees in here and 90 degrees in here, 135 degrees. Right, so these two conditions, the lengths are different, and the angle is 135 degrees. These rules completely characterize this plot. Right? Okay, so Dinkin came along and he worked out a way of encapsulating this information about the angles and lengths between the simple roots in terms of what we now call Dinkin diagrams. Okay. So, and these are rules that work for any rank Lie algebra. So even for higher rank Lie algebras, you have these rules that are imposed by the geometry of what you're constructing. So the rules are the following. For every simple root, write down a dot. So in our diagram for a rank 2 Lie algebra, we'll write down 2 dots. Denote the angles between the roots by connecting lines. So no line between the 2 roots means 90 degrees. 1 line means 120 degrees. 2 lines means 135 degrees. And 3 lines means 150 degrees. And these are the only possibilities coming from the geometry. When the simple roots come in 2 different lengths, the longer root is denoted by an open circle, and the shorter root is denoted by the filled dot. Okay. Now, there are at most 2 different lengths of simple roots for any given diagram. Right? So you'll never have a diagram that has one that's longer than the other. You'll never have 3 different lengths or more. They're only ever the same length, or one set will be longer than the other set. Okay. So I think that the best thing to do is to look at some examples, which will give you some sort of feel for how these are drawn. So let's do that. So this is the SU2 Lie algebra, and we have the root plot written down here, and we can of course bisect the plot by drawing a line through here. And so we'll call this the simple root. And so for every simple root, we write down a circle. So this is the Dinkin diagram representing SU2. Okay, next we have SU3, which we all know and love. So here are the simple roots as we, right? So we can bisect the plot. And it turns out that these 2 are the simple roots. If we add them together, we'll get this element here. And so there is 120 degrees between these 2 elements, right? And they're both the same length. Okay, so what we do is we draw in 1 line for 120 degrees, and we have 2 dots that are open. They're not filled because both of these roots are the same length. Okay. Then we have SU2 cross SU2, right? And so they're both the same length, both of these simple roots. Right? And there's 90 degrees between them. And so if we look at the Dinkin's rules, for 90 degrees, you put no line connecting them. Right? And this kind of makes sense when you think about it, because these 2 SU2s, they don't talk to each other. Right? The SU2s sit in singlet representations underneath one another. So this notation is nice. These are sort of unconnected SU2 algebras. This is a semi-simple algebra. And anytime you have a root plot with disconnected regions, what that means is that you have a direct sum of connected or of simple Lie algebras. Okay, so now SU5, we've already had a look at the simple roots here. These have 145 degrees between them, and they're both of different lengths. So the smaller simple root gets filled in, and we have two lines here indicating there's 135 degrees between them. Right. And then here's G2. So there's 150 degrees between them, and one is longer than the other. So one of these dots gets filled in, and the other is left open. And we have three lines. Right? And that's all of the rank 2 simple Lie algebras in Dinkin diagram form. Now, the nice thing is this just continues to work. You can just apply these same rules to higher and higher rank diagrams. And so you can classify all of the compact, simple, finite dimensional Lie algebras by their diagrams, and this is what Dinkin has done. So these are the Dinkin diagrams for all of the Lie algebras that we've been discussing up to this point. Right? So that the families can all be written in the following way. So SU, the special unitary groups have the following Dinkin diagrams. The special orthogonal groups with odd n, I guess, or odd m, they take the following form. Symplectic groups have the following corresponding Dinkin diagrams. The even special orthogonal groups take the following form, and then you have your 5 exceptional cases. Okay. Now, there's some really interesting things to note here, and in particular for small n, so for SU2, for example, the Dinkin diagram is just a single point, right? Now, for SO3, right, SO3, that's when n equals 1, that will also be a single point. And so what you see is that SU2 and SO3 have the same Dinkin diagram. And what that is telling you is that their Lie algebras are isomorphic to one another. And so you can start reading off some nice information purely from these Dinkin diagrams. Okay. All right, so that's Dinkin diagrams. That's all I want to say about those for now. And now I want to jump into using Dinkin diagrams to find subalgebras. Does anyone have any questions they want to ask before I move on? Yes?
Professor, how can I know that if this, like that symplectic 2n group, the two black dots are connected by a single line, which of them has a shorter length? How can I know that?
Okay, so the rule is the following. All of the ones that are filled in have the same length, right? Then all the ones that are not filled in have the same length. And so you can see that this object here is not connected directly by any line to this one, for example. And that means that they sit at 90 degrees to one another. Right? They're orthogonal to one another. Right, so
there is a semi-simple group, right? Not connected.
So this is a simple group because there are connections here, right? So if for example there was no connection here, then you'd get a semi-simple group. But all of the Dinkin diagrams that have connections between, if there is a connection between 1 and 2, and then between 2 and 3, and so on, then that corresponds to a simple Lie algebra.
Okay.
But so to give an example, so SU2 has 2 disconnected regions in the plot. So this is a semi-simple. This corresponds to a semi-simple Lie algebra.
So there will be no line connected between the adjacent dots. That will represent the semi-simple algebra.
Correct. So for example, if for example we had 1 dot here and then 2 dots connected to each other. So say for example we had 2 dots connected to each other like this, and then a separate one over here. That would correspond to a semi-simple Lie algebra SU2 plus SO5.
Okay. Thank you.
No worries. All right, so So now what I want to do is I want to jump into one of the most beautiful aspects of these plots, and I suppose one of the most useful aspects, and that is finding subalgebras. And I apologize, but I have to introduce some more language in order to do this. And so here are some important words that I'll be using through the remainder of the talk. So when I say an algebra is a subalgebra is maximal, what I mean is the following. If A prime is a subalgebra of A, then it's maximal if there's no other subalgebra A star, such that A prime is a subalgebra of A star. And so you can't fit this subalgebra within another subalgebra if it's maximal. Right. Now, in what I'm going to describe now, I'm going to be talking as much as possible about maximal subalgebras, because once you've found a maximal subalgebra, you can find any other subalgebras sort of in sequence, right? So I'll discuss for the most part just finding maximal subalgebras. Now, for the maximal subalgebras, they break up into two kinds, right? There are the regular subalgebras and the special subalgebras. Regular subalgebras, you can find them by looking directly at the root diagrams and directly at the Dinkin diagrams. Right? So these are the ones we're going to focus on. And then there are some special subalgebras, and these subalgebras you can't find directly by just looking at the Dinkin diagrams and root diagrams. You sort of have to still go in and play around with the commutation relations and structure constants. So these sort of, they're special in the sense that they're not immediately obvious subalgebras from the root diagrams. And so I'm not going to focus on these too much. I'm going to more focus on regular subalgebras. Okay, so let's have a look at an example. We've already seen an example, but so consider SU3, right? The Lie algebra SU3 has a maximal regular subalgebra SU2 plus U1. Given by the generators T1, T2, T3, and T8. Right, so this subalgebra corresponds to the SU2 subalgebra we already looked at, in addition to the remaining degenerate zero root here, which corresponds to a U1 generator. Right, so these highlighted elements here, including both elements at the origin, they form an SU2 plus U1 subalgebra of SU3, right? And notice that because we include this U1 element, this is non-semi-simple. So there's going to be two types of subalgebras. There's going to be semi-simple and non-semi-simple. And U1 is an abelian piece, so it's not semi-simple, right? Okay, so this is the obvious maximal subalgebra you can find in SU3 just by looking at the plot. But SU3 also has a special, so this is a normal subalgebra, but it also has a special subalgebra. Sorry, this is a regular subalgebra. But SU3 also has a special subalgebra, which is SU2, generated, for example, by T2, T5, and T7. Now, I'm not going to go back and show you the form of the structure constants, but this SU2 subalgebra is inequivalent to this SU2 subalgebra, right? There's no transformation that can take you from these three generators to these three SU2 generators up here, right? So they're inequivalent, right? This SU2 is not this SU2. It's a different one that you can only find by having a look at the structure constants, right? And so I just want to point out that there are occasionally cases where you can find these special maximal subalgebras, but I'm not going to focus on them. I'm going to focus on those subalgebras you can find just by looking at the root plots, because I promised you no more algebra this time. Okay, so let's have a look at G2. So here's an example. So G2 has two regular maximal subalgebras. Right? The first is the following one. Right? If we have a look at this plot, you can find that there's this SU2 root diagram sitting within the plot. Right? This is our SU2 subalgebra. Right, you can see this directly from the plot. And there's also an SU3 which sits in here, which you can find. You can read this directly off the plot just by having a look at the plot, essentially. Okay, there's also a special maximal subalgebra given by SU2, but again, I'm not going to go in and show you that because I'd have to describe all the structure constants, and I'm going to. So instead, I'm just going to focus on those that you can read off from the plot. Okay. Now, so this is how you use the root diagrams to find subalgebras. And so how do you do the same thing at the level of Dinkin diagrams? Well, there's a nice trick that you can use. So subalgebras will always come in two varieties. There's the regular, there's the non-simple, non-semi-simple subalgebras, which include a U1 part, right? And then there's the semi-simple subalgebras, which don't include a U1 part. So if you want to find the maximal non-semi-simple subalgebras, what you do is you start off with the Dinkin diagram that you're interested in, and you simply cross off one of the roots, right? And what you end up with is the root diagram for the semi-simple part, and then an additional U1 part comes. You sort of replace this root here with a U1 part. So this is the trick that you use, right? So for example, G2, you can cross off this root and you get a subalgebra SU2 plus U1. So SU3, you can do the same thing. You can start with your SU3 Dinkin diagram and cross off one of the roots. And what you end up with is a non-semi-simple Lie subalgebra SU2 plus U1. Now, I want to point out one thing that's important to note. And usually when you perform this procedure, the subalgebra that you get is maximal. But there are a few exceptional cases. So almost always the resulting subalgebra is maximal. I think the only cases when you're dealing occasionally with the exceptional groups. So for example, if you look at G2, when I've crossed off this element here, I get SU2 plus U1. But we see that G2 actually has an SU3 subalgebra, right? And this SU3 algebra itself has an SU2 cross U1 subalgebra. And so actually, this non-semi-simple Lie algebra actually sits within an SU3 subalgebra of G2. Right? So this happens not to be maximal, but almost always when you follow this procedure, you'll end up with a maximal subalgebra. There's only 5 exceptional cases, and I think they all turn up when you're looking at the exceptional Lie algebras. But this is a subalgebra, it's just not maximal in this special case. Okay, so that's fine. That's the trick that you use for finding non-semi-simple subalgebras. So you can take any of these Dinkin diagrams here and just cross off any of the roots that you like, and that will give you a resulting non-semi-simple Lie subalgebra. So, for example, SU4 has SU4 has these 3. So the SU4 diagram just has these 3 connected elements. If I remove the central guy, I'll get SU2 cross SU2, or SU2 plus SU2 rather as a sorry. Let me start again. If I start with SU4, that will have a Dinkin diagram with 3 roots. If I cut out the center one, then the resulting subalgebra will be SU2 plus SU2 plus U1. Okay, so I told you there are two types of maximal subalgebras. There's the non-semi-simple, and then there's the semi-simple. And to get the semi-simple subalgebras, the maximal semi-simple subalgebras, you have to perform another trick, and that's the following. Every Dinkin diagram has what's known as an extended Dinkin diagram. So the extended Dinkin diagram you get from adding in the most negative root. Right? So here is the root plot for G2, and this is the most negative root. Right? So what I mean by that is if you consider this simple root as being a creation operator, then its corresponding annihilation operator will send this element to the 0 vector. And similarly, the negative of this one, operator over here, will send you to the negative vector. So there are no positive roots that can act on this element there are no negative roots that can act on this element to send you to anything other than the 0 vector. So this is the lowest possible root in this representation, right? And so if you look, this root here is the shortest root, so we'll fill this in, and that gets a solid dot. Then there's 150 degrees between this root and this root, right? So I'll have 3 lines here, and this is the longer root. This guy's longer, so this becomes an open dot. And then this root down here is 90 degrees to this root here, so there's no line connecting these two, right? And then these two roots are the same length and have 120 degrees between them, so they're both open and have 1 line. So this is the extended G2 root diagram, and Dinkin gives you the full set. So these are the extended Dinkin diagrams, and these are useful because you can use the extended Dinkin diagrams to find the maximal semi-simple sub-Lie algebras of any given Lie algebra. And as far as I know, there are no exceptional cases here. So for example, if we write down the extended Dinkin diagram for G2, right, then if we cross off this element here, we end up with the SU3 Dinkin diagram. And if we cross off this element here, we end up with the SU2 plus SU2 semi-simple Dinkin diagram. Right? So this corresponds to these two subalgebras, right? With G2, we found this SU2 plus SU2 subalgebra, as well as this SU3 subalgebra, right? And these are found by, first of all, constructing the extended Dinkin diagram and just crossing off some of the roots. Right, so that's all I wanted to tell you about Dinkin diagrams for today. So now this would be a good opportunity. There's still half an hour, so if you have any questions, now would be an excellent time. And then next time I'm going to continue with more of an applications focused lecture. So let me know if you have any questions. Is anyone there?
Sumit Vishas. Have any questions, Sumit Vishas?
Yes, Professor. No. Professor?
Yes?
in your previous, in your note, can you please check something? I think there may be a printing mistake or typo in your first day lecture.
Yeah. Yep.
No, yesterday's lecture, I mean.
Oh, yes. Okay. Whereabouts?
The SU2 adjoint representation given rho T1 F.
This one here?
Yes. Yes. Is it okay? I mean, rho 3 T1, there should be non-vanishing element in 2, 3 and 3, 2 position, but
sorry, I can't hear what you're saying.
I mean, according to the definition, rho 3 Tijk is equal to epsilon Ijk.
Yeah.
Then rho 3 T1, there should be non-vanishing element in the position matrix 2, 3 and 3, 2. I mean, 1 and -1 should be in the 2, 3 position or 3, 2 position, right?
Oh, yes. Yeah, that's correct. So I'm a little bit sloppy here. Yes. So that's correct. So for the, I didn't actually check that. Yeah. It doesn't matter so much for the overall lecture, but yes. So these two elements should appear here and here, I think. And similarly here, these ones I think should appear where, here and here perhaps. But yes, that's correct.
Yes.
So yeah. So you should permute these guys in some fashion. Yes, that's correct.
Yes, and T2 maybe there is a minus sign above and +1.
That might be true as well. So yeah. So I've just been a little bit quick here. I didn't pay attention when I was writing these down. But yeah, that's correct. So if you actually try to calculate this, you'll find that the ones and minus signs appear in slightly different configurations. But yeah, thank you for pointing that out.
Thank you, Professor.
Does anyone have any further questions about today's lecture or yesterday's lecture for that matter?
Hello, sir.
Yes.
Can you please explain more about simple and semi-simple Lie algebra?
Oh, okay. So a simple Lie algebra. So I gave the definition all the way back here. Okay, so a semi-simple Lie algebra is a non-commuting Lie algebra, and the definition is it's a non-commuting Lie algebra that doesn't contain any non-zero proper ideals. Right. So what an ideal is, if you have some algebra element, if you have some algebra and some subset in that algebra is closed underneath underneath all the operations of all the other elements of the algebra, then you call that a proper ideal. Right? So in other words, if I have some element A in this proper ideal, and I act with any element in the algebra, any other element will map that A into some other element within the proper ideal. Right? So it's a little bit hard to show you without a blackboard. Oh, actually, I can draw it up. Can't I? What can you see if I open up a Paint document? Can you see this?
Yeah, it's visible.
Okay, so let me know if this is visible. So imagine I have all the elements of my algebra, my set. A proper idea is a subset, right, And if I act on this set with any other elements in the algebra, then this set remains closed. Right? That's a proper ideal. So for example, if I have some element in here, A, and some element in here, B, right, then A, B will be in here. Right? So if this is a proper ideal. So a simple Lie algebra is a Lie algebra that doesn't contain any non-zero proper ideals. Okay, so that's the definition.
So in this, in our normal context, AB will be basically the commutator of A and B, right?
Yes, that will be the commutator of A and B. That's exactly right. So my apologies. So for I'm being a bit too loose, but yeah, that should be written like this. I apologize. Right. So in particular, so a simple Lie algebra is a Lie algebra that doesn't contain anything like that. It doesn't contain any non-zero proper ideals. Now, a semi-simple Lie algebra is just a direct sum of simple Lie algebras. So, for example, SU2 plus SU2 is a semi-simple Lie algebra, right? Because it's the direct sum of two simple Lie algebras.
Can SO4 algebra called simple Lie algebra? Because the SU2 direct sum SU2 is isomorphic, locally isomorphic to SO4, no? Am I correct?
Let me have a look at that. So we can read that off the Dinkin diagrams here. So SO4, where are you? Okay, so SO4, we can come down and have a look. So SO4 will have two roots. So it will be this root here and this root here. And none of these other roots. So this will be the first root, and this will be the first root, and this will be the second root. So you'll end up with two roots that are disconnected from one another, right? And so indeed, SO4 is isomorphic to SU2 cross SU2. That's indeed correct, and you can read that off these Dinkin diagrams, in fact. Did that answer the question?
Yeah, thank you.
I think, Shane, yes, you can say
Yeah.
that the simple Lie algebra is the Lie algebraic version of the normal subgroup.
Yes.
Or invariant subgroup. G inverse will be again H. So when you consider Lie algebra, infinitesimal Lie algebraic version, the commutator of G with H will be again some element of H. Lie algebraic.
Yeah. Oh, yes. So yeah. So that's the so not simple, but the proper ideal is the algebraic version of what I guess is a normal subgroup in the group language.
Yeah.
So you said that I think direct sum of SU2 and the U1 is non-semi-simple because is it because U1 is not a simple Lie algebra?
That's exactly correct. So so mathematicians make definitions to make their lives easier. And so if you look at the definition of simple, they define it to be non-abelian, so a non-commuting Lie algebra. And I believe they make this definition just because it makes their life easier when they're working with various proofs. But yeah, so any direct sum between a semi-simple Lie algebra and U1 is non-semi-simple, just by definition.
Okay, sir. Thank you.
Professor.
Yeah.
Can you say something about the exceptional Lie algebra?
Can I say something about the exceptional Lie algebra?
I mean, the definition. Yes.
Any of these here?
Exceptional Lie algebras. Their definition or something. I mean. Yes.
Okay, so I want to be a bit careful because I think has Latham Boyle given his third lecture yet? I think Latham Boyle will touch on these exceptional groups.
Sorry.
I think Latham Boyle will touch on these exceptional groups in his next lecture. So I don't.
Okay. But today maybe he will talk about exceptional Lie algebra.
Yeah, but I can answer your question, but I don't want to answer it too thoroughly because I don't want to run into Latham's lecture. But what I will say is the following. So if we have a look at G2, right? G2 is the symmetry group of the Octonians. Are you familiar with the Octonians?
No, I'm not.
Okay, so the Octonians are a really interesting algebra. So just like you have the real numbers, you've got the real numbers and the complex numbers. So you get from the real numbers to the complex numbers by adding an imaginary element. And you get from the complex numbers to the quaternions by adding 2 more imaginary elements. Have you heard of the quaternions before?
Yes,
so the symmetries of the quaternions are SO3, right? The Lie algebra that acts on the quaternions, what you'd call the derivation algebra, is the same as SU2 or SO4, right? And so there's another I should draw this down here. Okay, can you see this diagram here? So this is a funny way to do it, but if we have so we have the real numbers, right, and we have the complex numbers. So the real numbers have one real number, and that's all. The complex numbers have I, so it's got you can construct them from real numbers and imaginary numbers. Then the quaternions have one real number and 3 imaginary numbers. And the Octonians are the next generalization. And they have 7 imaginary elements. So there's 1 real element, then there's 8 imaginary elements. And the symmetries of the quaternions is SO3, and the symmetries of the Octonians similarly is G2. So that's the simplest way to get G2 is as the symmetry group of this sort of more complicated set of numbers, the Octonians. And I think Latham's going to go into detail and explain to you what the Octonians are.
Okay.
Now, that's what G2 is. Now, F4 is also extraordinarily interesting. So, do you know what a Jordan algebra is?
No, Professor.
So,
Professor Latham will talk about Jordan algebra and the exceptional algebra.
So I can,
to this lecture.
I can tell you very briefly though. So a Lie algebra, in a Lie algebra, you take you start with anti-Hermitian elements A and B. You can think of these as being matrices, n by n anti-Hermitian matrices, and their product is given by the commutator. A Jordan algebra you can think of as being Hermitian matrices, where their product is given not by the commutator, but by the anti-commutator. Right? So Lie algebras and Jordan algebras are in some sense dual to one another. So in Lie algebras, you start with anti-Hermitian matrices and you equip them with the bracket to get an algebra. In Jordan algebras, you start with Hermitian matrices and you equip them with the anti-commutator to form a Jordan algebra. And there's a very, very special Jordan algebra, which is built as 3x3 matrices, where the entries are Octonian elements. Right, so this is a Hermitian.
One real and
the diagonal
8 complex number.
Well, these diagonal ones are real, and the off-diagonal ones are Octonian elements, right? And they're Hermitian. Now, this algebra here is a Jordan algebra if you equip it with this symmetrized matrix product. And it turns out that its symmetry group is F4. Okay, and these other groups can be found by some very interesting constructions. I'm not going to go any further because I think Latham will later on today be going into how to construct these in depth. So you'll get a lot more information from him. But yeah, so these more or less all relate in certain ways to the Octonian algebra.
Okay. And E8 is the in your first page you show a 2D projection of E8 root diagrams, right? There's the Dinkin diagram. Yes.
What's the question, sir?
No, I was just saying that the Dinkin diagram was drawn. Yes.
Yeah, that's exactly right. Yeah. So this is the largest of the exceptional groups. So this is the example I used at the beginning. So are there, does anyone have any further questions?
Hello?
Yes?
Yeah, I have one question.
Sure.
Hello. Are the simple roots unique?
Yes. So, well, it depends how I answer that question. So, in other words, when I bisected the roots, right, it's a conventional choice which roots I call positive and which ones I call negative. But once you've made that choice, they're unique. Yes.
I just wonder that on a two-dimensional plane, any two non-collinear vectors can be considered as the basis, right?
Yes, but so I guess the point is that you want to be able to form the rest of these guys. So the thing that's special about the simple roots is they can't be built from the other roots with positive coefficients.
Are zero coefficients allowed? Zero?
Yes. So for example, yeah, yes.
Okay. Okay, so it will not be possible to generate 1, 0 from other two vectors, right? If I choose in a different way as the simple roots.
Yeah, so that's correct. So if you start with if you try to construct this simple root from the remaining positive roots with only positive coefficients, you'll see that it's not possible.
Okay. Okay, thanks.
Positive means it should be integer valued or any fractional valued or anything can be allowed.
I actually don't know the answer to that. I think it's integer valued. I think that will always be the case in any. I think it's integer valued. In other words, I think the definition of the simple roots doesn't rely on integer or non-integer coefficients, but I think in practice, when you construct these roots from the other roots, you'll find that the coefficients are always, I think they'll always be integers, but I actually haven't checked that.
Could you kindly give a little more highlight to the angles you talked about? A revision, though it was certain extent it's clear, but a bit more emphasis on that may help.
Okay, so if you remembered to start with, we went through this procedure where we were looking. So we wanted to. So if you choose any SU2 subalgebra, for example, in this SO5 root diagram, then any other elements, any other roots that appear have to sit in appropriate representations underneath this subalgebra. And that's true for any of the subalgebras you choose, right? And this fact places extreme restrictions on where you can place these roots. Now, I haven't done the analysis myself, but what Dinkin showed, what he proved, was that the simple roots can only ever be separated by 90 degrees, 135 degrees, 150 degrees, and 120 degrees. So I haven't done that analysis myself, so I can't tell you how he does that proof, but it essentially comes from this geometry, and so what I mean by that angle is literally if you were to draw, if you draw a straight line from this root to the zero and this zero to this root, and just look at the angle between them, that's the angle I'm talking about. Is that what you're looking for?
Yes, that's okay, because we have to give some more time to analyze that. Technically, it's okay, sir. We are very happy, but we need some more time to digest it.
Okay.
At least I need. Thank you so much. Thank you so much.
No worries. Are there any further questions? Does anyone have anything else they'd like to ask? If no one has anything else they'd like to ask, then or maybe someone's is trying to ask something, but they've got their microphone turned off. I'm not sure. Okay, if there's no further questions, should we reconvene in half an hour for the next talk, or what's the plan?
Yeah, you can take a break for 15 minutes, 20 minutes, maybe, as you wish.
So should we just what time would be convenient for you? Should we start in You set the timer.
Normal time was 4 o'clock here, Indian Standard Time. I mean, half an hour later. But if you want to come back early, it must be okay with all the participants.
How about we take a half-hour break, and I'll come back at the usual time. So in half an hour.
That may be better.
Okay. So I'll see you all in half an hour then. Thank you for coming along.
We take a break for half an hour and then we assemble here again at 4 o'clock.
Okay, perfect. Thanks, everyone.
Thank you so much. Okay.